Okay, good day friends. Today we are going to solve this problem number 2, and right now let's start. A small wooden ball is attached by an inextensible thread of length 30 centimeters to the bottom of a cylindrical vessel filled with the water. The distance from the center of the bottom to the point where the thread is fixed is 20 centimeters. The vessel is rotated around a vertical axis passing through the center of the bottom. For what angular velocity of rotation will the thread deviate from the vertical by an angle 30 degrees? The acceleration due to gravity is 10 meters per second squared. Okay, so basically what we have here is this picture. We have a vessel which is filled with water to a certain level. And also we have a wooden ball, which is this brown ball, attached with a thread to the bottom of the vessel, but it is not exactly at the center. It's in radius of 20 centimeters away from the center, and the length of the thread is 30 centimeters. Okay, so that's what we have in this problem, and at a certain point, this vessel starts to rotate with certain angular velocity, and that's what we need to find in this problem. As you can see here, I have noted it. So what is the most important thing to find in this problem? So when this thing starts to rotate, we need to imagine this thing correctly. What will happen is such kind of thing that the surface of the water will curve like this. And if you ask me why, let's move to another figure. So let's look at this. Let's say this is a certain disk. Yeah, this is the view from side. Let me write it okay like this. This is view from side, and this is view from top. Yeah, okay, so when you rotate around, when the disk starts to rotate around its axis, and you sit on this disk, at a certain point, if the angular velocity is too high, you just fall away from the center of the disk. You fall from the disk. However, the question is, what is the force that pushes you outward, which causes you to go away from the disk? And the answer would be that it is not a force. Yeah, it would be strange because definitely we know that we would fall away from the disk, not to the disk, and if we fall away, then there is something what pushes us. But in fact, it is not so. There is no any force acting on us towards outside. Yeah, so basically what happens is that every time when we rotate, in fact we move with a tangential speed. In fact, we always try to go straight, and the same thing happens when we are in here, when we are in here, and in here. But every time the friction force, as you can see here, yeah, it causes us to stick to the floor of the disk, and our path gets curved. So that's how we rotate with the disk. However, if the angular velocity is too high, it means that at a certain point, friction force is not strong enough to hold us. And at a certain point, if this friction force cannot hold us, of course, we will just go away from the disk due to law of inertia, because we have this tangential speed, which is also really fast, and friction force does not hold anymore, and that's why we just go with inertia. We might go this trajectory, we might go somehow like this. It depends on two factors, like the quantity of this angular speed, and also the measure of this friction force, of course. Yep, or we can go like this. Yeah, so it depends on the situation, but it doesn't matter. The main point, what we are trying to prove is that due to inertia, we will just go away from the center. And the same thing, in fact, happens right here. Basically, in comparison with that situation, instead of the disk, we have this surface of the water. Let me draw it like this. And instead of the box or human being or anything, we have just the water molecules, and they start to push each other to the side. The same thing what happened in our disk situation. And in fact, when all of those molecules push each other, something like this happens. In fact, this molecule pushes its neighbor, it pushes its neighbor, and so on, until the molecule at the very edge is pressed by all the others. That's why the edges are increased in level and the center is decreased in level. Yeah, you can see this thing. Yeah, it's really interesting shape, because right now we can see something very interesting. Okay, first of all, let's try to understand what can we do with this. In fact, we can do some analysis using the dynamics, and yeah, we can identify the forces which are acting on our wooden ball. Basically, what will happen is something like this, but we are not sure. In fact, it's something like this might happen. Yeah, why not? Nobody can prove us wrong yet, but right now, let's prove this. This thing will be exactly like this. And when our vessel starts to rotate, it will always, this system will stay always like this. So in fact, this thing starts to rotate like this, our ball starts to rotate like this. In fact, it would be something like this from this position. Yeah, so every time it rotates something like this ball will always be very close in this radius towards the center. Yeah, so you see this thing, it will not deflect on other side. And let me prove you why. So the point is that first of all we've got this basic forces which are mg. We've also got just a tension force by the rope, and this is the basic stuff. But what's interesting, we can see this wooden ball going upward, yeah, basically because of it doesn't fall. And we know why. It's just the buoyancy force. It's the Archimedes principle. We know that. Yeah, buoyancy force. However, what is the force what makes this wooden ball deflect a little bit left? In fact, I would say that it is buoyancy force as well. Yeah, it's strange, but right now let's rethink our position about buoyancy force. Basically, what is the main principle of Archimedes principle? It comes from the pressure difference. In fact, let me choose some points like this. Yeah, let's choose this point above the wooden block and this point below the wooden block. In fact, both of those points have pressure. We know that by this formula, rho gh, and this h is not the height but the depth. So we know that pressure depends on the depth when we talk about the fluids. And the deeper we go, the pressure increases. We know that from the basic mechanics, fluid mechanics law. And right now we have the very same situation. Let's call this just P1. Yeah, let's call it just pressure 1, and let's call this thing pressure 2. And we know that there is a pressure difference. We can say definitely that pressure 2 is larger than pressure 1 because the depth is more than the pressure 1. And we know that there is a formula of pressure that is force divided by area. And we can apply the very same thing, this thing in here, right? So it will be something like this, just force 1 divided by area more than force 2 divided by area. So area is constant. It's the entire surface of our ball. That's why it's not changing, and it would be something like this. Force 1, force 2, I'm sorry. This is force 2, this is force 1. Force 2, force 1, and in here we have force 2 more than force 1. Yeah, so we have difference in forces. We know that force 2 is larger than force 1, and that difference in forces is delta F, and exactly what our buoyancy force is. So idea of buoyancy force comes from the pressure difference originally, right? However, what did I mean by saying that horizontal force that makes our wooden block deflect a little bit left than its axis is also buoyancy force? The thing is, we have the very same situation. Look at this. Every time when we were taught at school, what will happen? Like, what is the difference in pressure from the left side and the right side? And every time at school, we were told that it's the same because it doesn't depend if you go right, if you go left. It doesn't matter if you go forward or backward. Anyway, it will be the same pressure because it depends only on depth. However, in our situation, it's not a typical situation. If we look at this, yeah, let me choose some equal points, something like this, yeah. Yeah, they're equally distant from the wooden block. And look at this. This point, this depth is definitely smaller than this depth. So the face of our water is definitely curved, and that's why there is a difference in depth. So this, let me call this some pressure 3, this is pressure 4, this is height 3, let's call it, this is height 4. And we can see that there is a depth difference, that's why there is a pressure difference, and we can apply definitely the same thing. So if there is a pressure difference, there is definitely a force difference, the very same law which we applied right here. And if pressure 2 is larger than the pressure 3, it means there is some force difference, which is resultant force towards the left, and this is also buoyancy force. However, let's write it like FBY, this is FBX, so we don't mess it up, okay? Okay, so basically, I think that's all the things that we need. However, let me write one more thing, which is also very important. We know the law of Z from geometry, yeah? If this is alpha, then this is alpha. Yeah, this is the basic geometry principle, and also we have this thing. We can put Z anyhow we want, yeah? Let's do it like this. So this is Z as well. This is straight line, yeah? And if this is alpha, then this is alpha as well. So we can use the very same principle right here. This would be our alpha, okay? So you know how we work with tension force, which has two components, not one. Okay, so let's write the second law of Newton. So all the forces acting in vertical, all the forces acting in horizontal, and then let's apply Newton's second law, and so on. So basically, first of all, let's write for y, it would be F buoyancy, yeah? It doesn't matter from what we start because it's in equilibrium in vertical component, because it doesn't go up, it doesn't go down, it's in equilibrium. Okay, so it's F by minus mg because it is opposite to F by. And also we have here tension, yeah, you can see this, it has two components like this, and we know that the vertical component of the tension force is definitely T cosine alpha because it's adjacent, right? Okay, so it's just minus T cosine alpha equals 0 because there is no motion in vertical axis, right? Okay, so let's move to horizontal axis. Let's write like x, and here it is more important. We know that the rotation happens due to the center of the vessel. That's why that would be the main axis for us. So this line would be the most important line for our situation, yeah? This line. That's why we write everything dependent on this particular line. And that's why we need to write everything dependent on this line. So we have here angular velocity, and also when we rotate, as I've said before, our wooden ball would just rotate with the water like this, and this point will rotate like this ball will rotate like this, and every time it will look at the center of the vessel, yeah, central axis of the vessel. So basically this would be our centripetal acceleration, okay? So let me draw it like this. This is our centripetal acceleration. So you can see that our FBX is directed towards that centripetal acceleration. That's why we need to write it first. It would be positive because it looks towards the centripetal acceleration, yeah? So it would be our FBX minus what is opposite to it. It's, of course, the horizontal component of tension force, which is T sine alpha equals MAC, yeah, centripetal acceleration. Okay, so basically we cannot solve this problem easily. Why? Because we don't know what this, okay, I'm sorry, we don't know what this thing is, we don't know what this thing is, we don't know about tension force, we are not told anything about the mass, okay? However, we have only 2 equations and 4 unknowns. Mathematically, we cannot solve it easily. However, we know the formula of the buoyancy force, okay? So the thing is just ordinary, okay, let me write somewhere here, okay, it would be just rho Vg, yeah? Because we know that this thing is this thing. We know this formula, and it would be just, okay, let me delete it. It would be something like this, minus mg minus t cosine alpha equals 0, yeah? And let me just move this t cosine alpha towards that place, and it would be positive. Let me write it something just like this. It would be just something like this, right? Okay, so also we've got the common factor, which is g, and here we have rho v minus m, and t, we've got cosine alpha. We can move it just here downward, and it would be just divided by cosine alpha. Okay, that's the thing that I like. Right now we know what tension force is, and that's really important, to be honest, because we will use it a little bit later. Right now, let's look at the second equation. So basically what we have here, we can write the very same equation, but there is something to note. Okay, we can write again rho v, it's the same thing, in fact, the same density because it's the water, the volume, but we cannot apply here g because gravitational acceleration is only vertical. It does not affect a horizontal axis. That's why we have different acceleration which acts in horizontally, and we already know it. It's our centripetal acceleration, right? So that's why we write here that AC. Okay, good. And right now we can just write here T sine alpha equals MAC. Okay, we can move this MAC here, and we can move this T sine alpha here, and we will have something like this. Rho VAC minus MAC equals T sine alpha, right? And we have common factor, which is AC, rho V minus M equals T sine alpha. Okay, so basically, we can find the formula for centripetal acceleration. Okay, let's write it something like this. AC equals, what? We can move this thing entirely below T sine alpha, and we will have this thing. T sine alpha equals divided rho v minus m. Okay, good. And we already know what this tension force is. It is right here, and we can just apply it in here. And if we continue, it would be something like this. G here, rho v minus m. Sine alpha is still on the top. Okay, so cosine alpha goes to the bottom, and this thing is still on the bottom, rho v minus m. And as you can see, it is very comfortable because this thing and this thing, they just cancel out. We also know that sine alpha divided by cosine alpha is just g tangent alpha. Okay, so this thing is just simplifies into g tangent alpha. So this is really something very comfortable because we know that AC equals g tangent alpha. It's really comfortable. However, we're not told to find centripetal acceleration. We need to find angular velocity. However, we know the formula of angular velocity. Basically, what is centripetal acceleration? It's velocity squared divided by r. But we also have the formula of velocity, which is just as angular velocity multiplied by radius. And if we just apply this thing in here, it would be just AC equals omega squared, r squared divided by r. This thing cancels out, and we will have just omega squared r. Okay, so we can just apply this thing. Okay, let me draw, yeah, this thing, we can apply it just in here. So it would be just something like this. omega squared r equals g tangent alpha, yeah? Because basically our AC was g tangent alpha, and our AC is also omega squared multiplied radius. And that's why we need to find omega itself, and it would be just square root, because this is square and we need to get rid of that square. Radius goes below and it would be just g tangent alpha divided by r. However, it's not the final answer because we don't know what this r is, but in fact we do, because when this thing rotates, we need to find this little radius. Well, as I've said before, this thing, this wooden block, it rotates like this, yeah, like this. And when it rotates, we know this little radius, what this is, because in the beginning we are told that this thing is attached in the radius of 20 centimeters. We know this entire part, which is r, but also we know what this small part is, like this part. This is just L sine alpha. Why? Because this thing is L, and as you can see, this is alpha, and definitely this is L sine alpha. This is L sine alpha, and we can say that this thing is L sine alpha, and we can say definitely that r equals just this small r minus L sine alpha. Okay, this is the thing that we need, because we know r, we know L, we can apply it into our formula, and we will have just the final answer, which is angular velocity equals square root g tangent alpha divided by r minus L sine alpha. So basically, we do have this alpha, we do have r, we do have L, and the g is constant. That's why this is the final answer. We know everything, we can solve it, we have numbers, you can apply it yourself. I will not, because the main part, the physics, is done, and this is the right answer. Thanks for your attention, and if you have any questions, you can write me privately. Okay, goodbye.